Welcome to yet another class. I'm Dr. B, your chemistry teacher, and today we are going to be discussing the Jablonski diagram. What a sweet and comfortable nickname for someone. Certainly not me. Alright, so today we are going to be discussing Jablonski diagram, and under Jablonski diagram we will be talking about radiative and non-radiative transitions. Now this topic we are talking about here is under what you can comfortably call photochemistry. So under photochemical reactions, we can discuss comfortably radiative and non-radiative transitions using the Jablonski diagram in discussing it. Do not forget that in this class you have to share, you have to also subscribe. If you go to my YouTube channel, Dr. B chemistry classes, or rather science classes, you just need to tap the bell for subscription, and whenever these videos come up, they will get you will get a notification. And do not forget to share, tell your friends to also do what? To also subscribe immediately the videos are shared to them. The first Facebook page, you also have Dr. B science classes. When you go there, don't forget to follow. And when you share, you can also ask them to follow as well. And do not also forget to leave your questions in the form of comments, and we will do justice to them. Alright, now when we talk about Jablonski diagram, but let us first have an overview of what photochemical reactions are. Do you know that photochemical reactions are different from thermal reactions? Photochemical reactions are completely different from thermal reactions, while photochemical reactions have much to do with radiations, have much to do with light. Thermal reactions can take place in both light and dark conditions. Now, the photochemical reactions are specifically reactions that come about by the presence of light radiation. So here, radiations are very pertinent, and that is why photochemical reactions are always taking place around the UV visible region of the electromagnetic radiation. Electromagnetic table. Now, when you look at the AMR room, you will see that between 2,000 to 8,000 Armstrong, or about 170 to about 320 nanometer, you find radiations that are UV or visible, ultraviolet or visible. And at this region, it is believed that when such reactions are released, there is a tendency for what? For excitation or absorption and possible excitation or activation of molecules described as photons. So usually in photochemical reactions, photons are what you expect as the pertinent molecules that will be experienced. Now why we agree that photochemical reactions are quite different from thermal reactions, you could see that photochemical reactions are at the region of just very light radiations. But thermal reaction needs so much of heat for chemical reactions to take place. Now, photochemical reactions are always being noticed in application, everyday application. You find photochemical reaction, and a very quick one is in the photosynthesis. Okay, so you have heard about photosynthesis, where of course plants generate their foods through the mitochondria by using sunlight and water. The presence of sunlight already let you know that it requires what? Radiations. It requires absorption of radiation and possible what? Excitation or activation of photons that come with what? That come with such radiations. And that is a typical example of what? Of photochemical reactions. You can also see them applicable in your current television screens. In your television screens are possibly showing or coming with those lights because of the presence of photochemical reactions that take place there. And also in your fluorescent tubes, you could also find photochemical reactions taking place there. And that is because of the presence of phosphorescence and fluorescence. So the phosphorescence and fluorescence are actually the consequences of radiative transitions, and that is applicable in your television screens and also in your fluorescent tubes. You can also find this process, okay, in the synthesis of vitamin D. So when you see the process by which vitamin D is being produced, okay, or is being synthesized, the process, the paramount implications is from the photochemical reaction process. Okay, and you can go on and on and on. And how about in your uh, production of monomers of nylon 6? How we know that or people will know that nylon 6 is the basic monomer in the production of nylons, caprolactam. So caprolactam is the synthesis of caprolactam, which is a basic monomer for nylon 6, is also following the process of photochemical reactions. We can go on and on and on and on. There are some other synthesis of certain chemicals that involves photochemical reactions. Now, everything about photochemical reactions is embodied in the Jablonski diagram. You can possibly explain photochemical reaction comfortably if you understand the processes involved in the Jablonski diagram, and that is why I felt we should talk about it. Alright, now when you see a typical photochemical reaction, okay, it is based on absorption of radiation, like I said before. The basic principle of photochemical reaction or photochemistry is on the absorption of radiation. So whenever you have a monochromatic radiation or a monochromatic light, you allow it to pass through a homogeneous mixture. Alright, you will notice that the radiation that goes into or goes through that mixture will have three different channels or effects. One is that radiation that goes to that particular substance, homogeneous mixture of substance, will either do what? Be absorbed, or it will be what? It will be transmitted, or that radiation will rather be reflected. Okay, so it's either the radiation is absorbed or that monochromatic light that you put in to that sample is transmitted, or it is what? It is simply reflected. But in photochemistry, the radiation that is of importance, that we are concerned with, is the radiation that is absorbed, because it is that radiation that is absorbed that allows for activation, okay, that activation or excitation of what? Of photons in the course of a chemical reaction, where you could now have the radiative and non-radiative transitions taking place. So the basic analogy here is for you to have radiative transitions or non-radiative transitions taking place in the course of a photochemical reaction, there must be radiations that are absorbed. Now we're going to look at the principle of photochemistry and also look at how we can possibly put up the diagram, okay, that governs the principle and instrumentation of photochemistry that borders on photochemistry in our subsequent classes. But today, let us see how we can be able to do justice to the Jablonski diagram. Now, something you must understand is that we have just mentioned that radiations that are absorbed are the radiations that allow for what? Allow for activation or excitation of what? Of molecules or photons in the course of a photochemical reaction. I don't want us to miss the fact that photochemical reactions are reactions that does not depend on temperature totally. In fact, they depend very less on temperature. Unlike thermal reactions that depend seriously on temperature because they depend on heat. These ones depend on light, not on heat energy, but just on light energy. And you also have to understand that the Gibbs free energy that determines continuity of reactions and stability of reactions for photochemical reactions is always negative and positive at the same time. So you can either have it negative or have it positive, describing the nature of stability in terms of stability or the nature in terms of feasibility, okay, or spontaneity of photochemical reactions. Unlike in thermal reactions where you can only have thermal reactions showing Gibbs free energy to be what? To be negative. Talking about what? Talking about spontaneity of such reactions. Now, let us look at the Jablonski diagram. If you take a look at this diagram, you'll notice that this diagram has some letters and numbers that are written everywhere around it. But let us take it gently. If you take a look at this S that you see here is simply described as singlet state. Okay, so this S that is seen here is singlet. This is singlet state. So this is the ground state, singlet state. This is the first energy level, singlet state. Second energy level, singlet state. Third energy level, singlet state. And you could have different energy levels as you go. And then this T that is here is described as a triplet state. The T is described as a triplet state. So you also have the triplet state ground energy level, you have the triplet state first energy level until the triplet state third energy level. And all these states, whether singlet state or triplet state, play significant role in describing the Jablonski diagram, where we want to study the excitation or the activation of photons or molecules in the process of the chemical reaction. Okay, now when you take a look at inside here, we have arrows written here. So what are these arrows? Okay, what are these arrows? So these arrows simply means relaxation. The arrows that you see here, this arrow you see here simply means relaxation. It simply means relaxation. That's what the arrows mean, relaxation. The IC you find here, look at IC, look at IC, look at IC, look at IC. The IC you find here is simply called internal conversion. The IC you see here is called internal conversion. And the ISC that you see here is the intersystem crossing. So you can, this is the intersystem crossing. Intersystem crossing, ISC. And the IC is simply described as your internal conversion. Internal conversion. Okay. So I want us to understand what these abbreviations are writing here mean. This is simply singlet states from the ground state energy level for the singlet state energy level, and then the first, second, and the T is the triplet state, begin from the ground state to the first energy level up to the third energy level, and the arrow means relaxation, and then the IC means internal conversion, where the ISC simply means intersystem crossing. And we're going to see the impact of these things we are talking about here. Now, when you have a molecule or a photon at this energy level, which of course is the the ground state energy level, singlet state energy level, and it gains radiation. It gains radiation, okay, from the sun, or perhaps, or from any source that can give us radiation around 2,000 to 8,000 Armstrong, or 170 to 320 nanometer at the UV visible region level. If it acquires such a radiation, it is going to do what? It's going to activate that particular molecule at the ground energy level here to do what? To move. And that's why you see we have HV absorption. And usually this radiation that will allow for, this UV radiation that will allow for the molecule at the ground state energy level to be excited will take just about 10 raised to power minus 15 seconds, and that molecule or photon will be excited. Now, as soon as it is excited, it moves to where? To the first energy level at the singlet state. It might at this point in time decide to do what? Decide to lose energy and fall back to the ground state. Now, if the molecule was at the first singlet state energy level and decide to lose energy, or in a process, the supply of the UV visible radiation is not that much again to move it to the next energy level, and it decides to fall back to the ground state, it is going to emit light, and the light is going to emit is what you call fluorescence. And usually this fluorescence, which is the light emitted when a particular photon or molecule lose energy and decide, or lose light and decide to do what? Or radiation to fall back to the SO, is always called what? Fluorescence. And this fluorescence is always called allowed transitions. They're always called what? Allowed transitions. Now, allowed transition because these transitions at this point in time takes only about 10 raised to the power minus 6 or 10 raised to the power minus 8 seconds for it to occur. So once it goes up from S0 to S1 and loses energy or radiation immediately, it falls within 10 minus 6 seconds. So it's as a flash. And that is why it is possible for you to have fluorescent bulbs and to also have your television screen showing with the lighting that you see. because that fall in transition is that fast and quick that as the molecule continue to fall from the S1 down to the SO, they emit that radiation as fast as possible, and it gives you a fluorescence. Now, if this particular molecule decides to rise, gain enough energy, and rises from here, moves all the way to S2 or S3, it will definitely again lose radiation and then fall again. If it falls from S3 to S2, or from S3 to S1, or from S2 to S1, certainly not from S1 to S0, the falling from S3 to S1 or S2 to S1, that is at their singlet state at the different energy level, is described as what? Internal conversion. So at any point there is a relaxation, there is always bound to be loss in energy or loss in light radiation, and the photon or molecule is bound to do what? To fall from this energy level to another, or from this to 1, or even from 2 to 1. And if it falls from 3 to 1 or 2 to 1, what kind of transition you are experiencing at that point is an internal conversion. Okay, that's what happened around here. Now let us look at what happened around here. That is around this particular region. But before we go there, let us also look at what we see here. There is a process where you can have a crossing of the photon that loses energy and decide to fall from a particular higher level to the next. Sometimes there's a crossing. And when this particular photon falls from, it's activated and excited and it loses energy and then it chooses to fall. If it falls and decides to cross from T1, which is a triplet state, down to S0 instead, it also emits radiation or light and is called phosphorescence. And usually phosphorescence happens around 10 raised to the power minus 9 to 10 raised to the power minus 6 seconds. But it's not that fast like fluorescence itself. No wonder it's called phosphorescence. So that is how fluorescence happens. Now, you can also see that relaxations are always about 10 raised to the power minus 10 raised to the power minus 12 to 10 raised to the power minus 10 seconds, which means that the relaxation process is also a bit fast, but not faster than fluorescent process. So every relaxation will always give rise to a particular transition. Okay, now at this point here, we also have internal conversions at this point, where we had agreed that internal conversions will always come as a result of what? As a result of a fall of a molecule or a photon that loses energy from either the triple state 3 energy level or to the triple state 1 energy level, or from the triple state second energy level to the triple state energy level. Now, once there is a fall of a photon or a molecule from this higher energy level to 1, or from 2 to 1, you are going to have an internal conversion which will take place. Internal conversion transitions which will take place. And there is always an emission of light in the process. But where you have the transition from this particular T1, triple state 1, going to S0, or even triple state 1 crossing to the single state 1, you always have an intersystem crossing that is going to take place. And usually intersystem crossing takes about 10 raised to the power minus 11 to 10 raised to the power minus 6 seconds. Now let us bring ourselves back. What are radiative and non-radiative transitions? From their explanation, I'm sure you have an idea already. Now, radiative transitions are usually transitions that are described as emission transitions. Radiative transitions are emission transitions, while non-radiative transitions are always seen as what? As heat transitions. There are no emissions in non-radiative transitions. No wonder they are described as non-radiative. Now, radiative transitions are transitions that take place with what? With an emission of radiation. That is just it. Radiative transitions are radiations that take place or occur with the emission of radiation. And usually there are two basic types of radiative transition, and those two types are fluorescence and phosphorescence. Now it has brought us to that understanding when I was explaining this. Now radiative transitions are transitions that are involved, that involve or that occur with what? With emission of what? Radiations. And these are usually fluorescence and phosphorescence. And remember that fluorescence transitions are the ones that occur at about 10 to the minus 6 seconds when a molecule or photon loses what? Loses light or radiation and choose to fall from S1 to S0. While the phosphorescent transition will also give out light when it loses energy and decide to fall from the triple state to the singlet state. So there are two basic types of radiative transitions that will always give out what? Light or radiation or emission of radiation at in the course of their fall from the high energy level to the lowest energy level, and that is the fluorescence and phosphorescence. Now, non-radiative transitions are transitions that take place without transmission of emissions. There are no emission of radiations, rather. There are no emissions of radiation for non-radiative transitions. There are no what? Emission of what? Radiation. Now, those particular ones will not give out what? Will not give out light. Now, those kind of non-radiative transitions are the ones we call internal conversion and what? Inter-system crossing. So, inter-system crossing and internal conversion are also radiation. Are also, of course, they are also transitions, but it's just that they do not emit radiation at the end of the day. But the most important of these two are the radiative transitions, because like I've mentioned, so many of those examples or applications I've mentioned make use of what? Radiative what? Transitions. That is the fluorescence and the phosphorescence. But it doesn't mean that we do not have also applications where internal conversion and inter-system crossing that belong to non-radiative transitions are applied. They are also everywhere. So in the course of our lecture today, I want to believe that you have understood so much about the Jablonski diagram in its use to explain radiative and non-radiative transitions. I'm glad that we are able to do justice to this particular topic today. Now I'm going to give you something to go and study to have a better understanding. Now, that thing you're going to go and study is called cold light. Cold light. So, you're going to read on cold light. Okay, read on cold light and types. Yes. Read on cold light and types. Surprisingly, you're asking, what is cold light? What are we talking about? Cold light. What are cold lights? It is there. Research on it, read on cold lights and their types. It will help you to understand more about radiative and non-radiative transitions. Now, until next time, do not forget to share, do not forget to subscribe, do not forget to leave your comments and like as well, both in the YouTube and in the Facebook page, Dr. B Science Classes. And until next time, it is bye for now.